Hello and welcome to section 6.3. Today we're going to talk about how to decompose a vector into an orthogonal projection onto W plus an element of W perp. So this is kind of an extension of what we did where we were looking at the span of just one vector. Now we're looking for a projection onto a whole subspace. And so kind of here is the idea. If we have a space, like let's say we're in R3 and we have some sort of plane in there, then what happens is that plane maybe is W. We'll think of it as the flat, in this particular picture, think of it as the flat XY axis, and maybe it's the span of two vectors, and then we have a third vector, a vector y, and we want to drop y down into W and write y as a vector in W plus a vector pointing straight out of W. So that's the picture that you want to have in your mind. And the way we do this is we have a formula that's just like the projection of y onto one vector, except we do it for all the vectors in our subspace W. And then the vector y hat is called the orthogonal projection, and we get for free that the vector z, that's y minus y hat, is actually in W perp. So, which remember, W perp is the set of all vectors that are perpendicular to or orthogonal to the vectors in W. So their dot product with anything in W is 0. Okay, so let's just do this by following this formula then. So y hat is given by, we first take the dot product of y with our first vector in our basis for W over its dot product with itself, and then we multiply that. So that's going to give us a number, a fraction, and we multiply that by the vector. And then we do the same thing for y with the second vector, -1, 3, -2 here, and we dot that with itself, and then times the vector. And so when we do this out on top, we get -1 plus 4 plus 3 over, because I just multiply the ones together, or sorry, the 1 with the -1. I'll do this next one more slowly just in case we've forgotten about how we do dot products. So we do 1 times 1, which is 1, 4 times 3, which is 12, and 3 times -2, which gives us -6. And then on bottom, we get -1 times -1, 3 times 3, and -2 times -2. And all that times that vector, and then we make nice pretty numbers that work out all right for you guys, and we end up getting 6/3 times 111 plus 7/14 times -132, which gives us 222 plus -1/2, 3, let's see, 3 times 1/2, so 3 halves, and -1/2 plus, sorry, -1 plus, okay, 3 halves, and then 1/2 times -2, which gives us -1. And then if we want z, we do our original vector y minus, oops, I didn't finish adding this together. So we have 2 minus 1/2 is 3 halves, right? 4 halves minus 1/2. 4 halves plus 3 halves is 7 halves, and 2 minus 1 is 1. Then to get z, we take y and we subtract out y hat, and we're left with -5 halves, 8 halves minus 7 halves, and 2. Okay. Now, our next question asks us to, in fact, show that this vector is in WPerp. So first, to do that, we need to check that the dot product of our new vector with each of our old vectors actually is, in fact, 0. So for this first one, we get negative 5/2 times 1 plus 1/2 times 1 plus 1 times 2, which is negative 4/2 plus 2, which is 0. And then we also need to check that dot product with our second vector, which was negative 1, 3, negative 2. And we get 5/2 plus 3/2 minus 4, which is 8/2 minus 4, so that's 0. And so Z is in fact in WPerp. And actually, if you want to test it in general, what you can do is you take this, this difference, so Z equals Y minus Y hat, and so that's, you plug in that formula, Y dot U1 over U1 dot U1 times U1, and you will see that you wind up getting, so if you take that and you dot it with any one of these vectors, you wind up getting 0. So try Z dot U1. Try that for yourself and you'll see. So that's basically taking this whole thing and dotting it with U1. And what's going to end up happening, well, actually, maybe I will talk this through a little bit more. So that U1 through UP is orthogonal. So let's go ahead and do this. So we have Y minus all of this stuff and we're dotting that, oops, okay. So we have Y minus this thing dotted with, let's just try U1. Then that equals, we can distribute that U1. So we have Y dot U1 minus, and then we have Y dot U1 over U1 dot U1 times U1 minus each of these components, UP dot UP times the vector UP dotted with U1. And the thing is that because this basis is orthogonal, these dot products are zeros. And so all of them are zeros except for that very first one. But here, ooh, and I forgot to actually do the dot product there. So, right, because this was, all of this is dotted with U1. So just so that, in case that wasn't clear. And this thing dotted with U1. So this is that thing and then dotted with U1. But now we can cancel out the U1 dot U1. And so we are actually left with Y dot U1 minus Y dot U1, and that equals 0. Okay, so now what's going to be important, and this is really crucial for 6.5. So at 6.5, we'll pull this all together and find a use for it. So you have to bear with me with a few more definitions for now. But what we want is we want kind of the closest vector of Y to our subspace W. So what's happening here is that when we think about Y hat is actually closer to this vector Y than any other vector in W. And so ultimately, if you're asked for the closest approximation, or the best approximation, the closest point in a space to a vector, you just take that orthogonal projection of your point onto, or your vector onto that space. So again, we use the same formula that we used up above. So I'm doing this a little bit faster. And actually what I recommend you do is pause the video, because I only have one quiz question in this video. Pause the video, try to compute this, and then come back and see if you got the right answer. We've now written most of it out. And if you do your math out, you should end up with -1,539. And so this means if I take y minus that new vector and I take the length, that distance formula, then that's going to be smaller than the distance to any other vector in W. So if I take y and I look at the distance between y and y hat, that's smaller than, and it's strictly smaller than the distance between y and any other vector in W. And our first quiz asks you to actually compute this, which is called the distance from y to, in fact, the subspace W. Okay, so finally, if we have an orthogonal basis, then here is our formula that we just had up above. We just used this. But if that basis is orthonormal, then we have something even better. Each of these u1.u1s is just a 1. And so that means now if we have an orthonormal basis, our formula for y hat gets a little easier to compute. We just have the dot products of y and each of our vectors, each of our orthonormal basis vectors. If you like whole numbers, this is kind of nice. If your basis vectors and your y are already whole numbers, then you know you're not going to get any fractions because you've gotten rid of the denominator. But it will also see why this just makes some of our computations that we'll want to do for least squares fits, which is where we're going with this. So we'll see the utility in what we've done today, and earlier on in chapter 6 we'll see that in section 6.5 as we find lines of best fit for data sets.